Convolutional neural networks are a type of deep learning algorithm that have revolutionized the field of computer vision and image processing. They are specifically designed to process data with a grid-like structure, such as images, by emulating the behavior of neurons in the visual cortex of the human brain. The foundations of convolutional neural networks can be traced back to the 1960s with the work of neurophysiologists David Hubel and Torsten Wiesel. In 1959, they began studying the visual processing system in cats, which led to their groundbreaking discoveries on the receptive fields of neurons in the visual cortex. Hubel and Wiesel published their seminal paper in 1962, describing the hierarchical organization of neurons and their receptive fields, which laid the groundwork for understanding the visual system. In 1980, Kunihiko Fukushima introduced the concept of a neocognitron, a hierarchical artificial neural network model inspired by Hubel and Wiesel's work. The neocognitron aimed to mimic the visual recognition processes in humans. Fukushima published his paper titled Neocognitron, a self-organizing neural network model for a mechanism of pattern recognition unaffected by shift in position, in the Biological Cybernetics Journal. However, it was not until 1989 when Yann LeCun, along with Yoshua Bengio and others, introduced a practical implementation of convolutional neural networks known as LeNet 5. LeNet 5 is a pioneering convolutional neural network architecture. It is widely regarded as one of the earliest successful implementations of convolutional neural networks for computer vision tasks, and played a significant role in establishing the foundations of modern deep learning. LeNet 5 was primarily designed for handwritten digit recognition, aiming to achieve high accuracy in recognizing hand-drawn digits from the famous MNIST dataset. The architecture consists of 7 layers, including 3 convolutional layers, 2 subsampling layers, also known as pooling layers, and 2 fully connected layers. The first layer of LeNet 5 is a convolutional layer, which performs the initial feature extraction from the input image. It convolves the input image with a set of learnable filters, also called kernels, to generate a set of feature maps. The filters in the convolutional layer are small in spatial extent but extend across the full depth of the input volume. The output of the convolutional layer is then passed through a nonlinear activation function, typically a rectified linear unit, ReLU, to introduce nonlinearity into the network. Following the first convolutional layer, LeNet 5 incorporates a subsampling layer, specifically a max pooling layer. The max pooling layer reduces the spatial dimensions of the input feature maps while retaining the most salient features. It achieves this by dividing the input feature maps into non-overlapping regions and taking the maximum value within each region. This downsampling operation helps to make the network more robust to slight spatial translations of the input. The second and third layers of LeNet 5 repeat the pattern of a convolutional layer followed by a max pooling layer. These additional layers allow the network to capture more complex and abstract features from the input image, gradually building a hierarchical representation. After the final subsampling layer, LeNet 5 transitions to fully connected layers, which are traditional artificial neural network layers where each neuron is connected to all the neurons in the previous layer. The fourth and fifth layers of LeNet 5 are fully connected layers that process the high-level features extracted by the preceding convolutional and subsampling layers. These fully connected layers serve as classifiers, making predictions based on the learned features. The last 2 layers of LeNet 5 include a fully connected layer with 84 neurons and the output layer with 10 neurons, corresponding to the 10 possible classes in the MNIST dataset, digits from 0 to 9. The final layer employs the softmax activation function to produce a probability distribution over the classes, indicating the network's confidence in each possible digit. Training LeNet-5 involves optimizing the weights and biases of the network to minimize the prediction error. This is typically done using the backpropagation algorithm, which calculates the gradients of the network's parameters with respect to a given loss function. The optimization is performed through an iterative process, where the network's parameters are adjusted using gradient descent or its variance. LeNet-5 demonstrated remarkable performance on handwritten digit recognition tasks, achieving state-of-the-art results at the time of its introduction. Its success paved the way for the broader adoption of convolutional neural networks in computer vision, and inspired further advancements in the field. LeNet-5's impact extends beyond its immediate achievements, as many subsequent convolutional neural network architectures built upon its principles and expanded on its concepts. While LeNet-5 was initially developed for digit recognition, its underlying principles and architectural elements are applicable to various computer vision tasks. The concepts of convolutional layers, max pooling layers, and the hierarchical representation of features have become fundamental building blocks in modern convolutional neural network architectures. Researchers have since developed more complex and powerful convolutional neural network models for a wide range of applications, but LeNet-5 remains a cornerstone in the development of convolutional neural networks, and a testament to the effectiveness of deep learning approaches in computer vision.